Section 2 is Taylor series. Yay! Do you remember Taylor series? Well, let me help you remember. The Taylor series of f at x naught is f of x is given by sigma, where sigma starts at 0 through infinity, of an times x minus x naught to the nth power. So this is a Taylor series, and it's f at x naught. That's where this x naught, that x naught will be a constant, right? Where, what does an stand for? An is the nth derivative of f evaluated at x naught over n factorial. Now, I'll show this expanded out in just a second, but if x naught is 0, then we call it the Maclaurin series. For f. So whoever this Maclaurin dude was, he came in and was like, oh, if it's centered at 0, then call it after me instead of Taylor. Okay, so what does this mean? This means that the Taylor series will be, if you start by plugging in a 0, you got a sub 0. Well, that means that it's this guy. So let's do that. I'll go. Okay, so really, here's what the Taylor series is. It is the nth derivative of f evaluated at x naught over n factorial, and then times x minus x naught to the nth power. Okay, so what does that mean? When you start with a 0, that means that you're taking the 0th derivative. Okay, that's just f. So f of x naught over 0 factorial. Remember, 0 factorial is just 1. And then times x minus x naught to the 0 power. Yeah. So what you start off with is your very first term will just be f at x naught. And then the sigma notation means plus. And then you'll take the first derivative at x naught over 1 factorial times x minus x naught to the power of 1. All right. Well, that just ends up being a first derivative. 1 factorial is just 1, and then times x minus x naught. And then the sigma says put a plus sign. And then you'll take the second derivative at x naught over 2 factorial times x minus x naught squared this time. That would be your next term, right? And you keep on going. Right? I don't need to, there's no simplifying that anymore. Well, 2 factorial is just 2, but you keep on going. That's how we would do the Taylor series. And if you remember, I had told you last year, or Mrs. Fox told you last year, that your calculator, even your graphing calculator, only knows how to add and subtract and multiply and divide. And so it would take a function like e to the x, and it doesn't truly have it memorized. Instead, what it has is it turns it into this polynomial. It turns it into this Taylor series, and then computes it that way. Okay, so let's do an example. We're going to find the Taylor series for f of x is equal to negative 1 over x about the point x naught equals negative 1. So about your center is going to be at negative 1. All right, so first start off by going, okay, f of x is just negative 1 over x. So what is f of x naught? What would f of negative 1 be? Well, it would just be negative 1 over negative 1. So that's a positive 1. Then you take the first derivative. Now, I highly recommend that you turn this negative 1 over x into negative x to the power of negative 1, because then when you do the pop and drop, it's pretty easy, right? So this is a pop that negative 1 in front, it becomes a positive, and then it's x to the negative 2, right? And so your first derivative at negative 1, when you plug a negative 1 in there, this is like 1 over x squared. So it's a 1 over negative 1 squared, which is definitely a positive 1. Taking the second derivative, pop and drop this guy. That would be a negative 2 x to the negative 3, which is negative 2 over x cubed. And so second derivative at negative 1 would be a negative 2 over negative 1 cubed. Negative 1 cubed is a negative. And so you end up with a positive 2. Did it say how many it wanted? Let's go. Let's definitely do at least the third degree. All right, so third derivative at x would be popping this guy in front. A negative times negative 3 makes it a positive 3, x to the negative 4, which is a 3 over x to the 4th. So the third derivative, evaluated at negative 1, would be a 3 over negative 1 to the 4th, which is a positive, lying to you. Negative 3 times negative 2 is a positive 6. Because I know how to multiply. Sure. Sure you do. Okay. Negative 3 times negative 2 is a positive 6. So a positive 6 and a positive 6. Okay, so there we go. 6. Perfect. What would the nth derivative be? You could keep on going, right? The nth derivative of this guy would end up being, do you see the pattern? We got a negative and then a positive, and then a negative and then a positive. So that means I've got a negative 1 to the, it started with a negative here. So we're starting with, yeah, n plus 1. If we're starting with an n equals 0. And then it would be where we got negative, and then with each of these guys, it ended up being an n factorial. It's 2 factorial, 3 factorial is 6. Yeah, and then times an x to the, when you plugged in a 0, you got negative 1, and then when it was a 1, it was a 2, because it's like your n is a 0 here, and then a 1, and then a 2, and then a 3 when n is 3. And so it's a negative, but then n plus 1 power. That makes sense? Yeah. And so what would the nth derivative at negative 1 be? Well, it would be you're plugging in the negative 1 into x, right? And so it would be negative 1 to the n plus 1 power, n factorial, and then times a negative 1 to the n negative n plus 1. Plugged in just the negative 1 into the x. I know we're mixing x's and n's, but what you're plugging in there is an x. All right, we can simplify this. This is, both of these have a base of negative 1, so it's a negative 1 to the n plus 1 minus n minus 1, and then times an n factorial. And so you end up just with n factorial is just each of these nth derivatives evaluated at negative 1. Okay, so remember your Taylor series is sigma from n equals 0 to infinity of the nth derivative at x naught all over n factorial times x minus x naught to the nth power. And so this guy ends up being, we're plugging in a negative 1 into your x naught. Not a fan of this pen. It is smearing all over. All right, n equals 0. It's a nice writer, though. F, the nth derivative at negative 1 over n factorial, x minus negative 1 to the nth power. Yeah. And so, what do we get here? This is, we just figured out that the nth derivative at negative 1 was n factorial. So let's replace that. That's n factorial over, I still have an n factorial there, times x. This is a plus 1 to the nth power. But, so keep in mind, what I did here was replaced this guy, what we said was that, replaced it with n factorial, but then you're dividing by n factorial, so those guys just end up canceling, and so the Taylor series for this guy is n equals 0 to infinity of x plus 1 to the nth power. Too bad. Okay. And you're going to start by expanding it out, and then taking each of the derivatives and all of that. If it's crazy, right? If it's totally crazy, what you could do also, so I did this totally using all these symbols and sigma and all of that. What you could have done, go back up to here. So I did this in the general sense, but you definitely, if I would have started with these guys, then that means f of x is equal to, remember it's f of x naught, and then it's f prime at x naught times x minus x naught to the power of 1 plus the second derivative at x naught times x over 2 factorial times x minus x naught squared, and then plus the third derivative at x naught times x minus x naught cubed over 3 factorial, and you keep on building it that way. And we found all of these guys, right? So that means that your f of x is, it's a 1 plus the first derivative here, 1 times x minus negative 1 to the power of 1, plus the second derivative was a 2, so it would be 2 over 2 factorial times x plus 1 squared, plus the third derivative we found was 6, so 6 over 3 factorial times x minus negative 1 cubed, plus, and it would keep on going like that, right? And so you would just simplify and go 1 plus x plus 1 plus, oh look, that canceled, x plus 1 quantity squared plus 3 factorial is a 6, so those cancel, and you got x plus 1 cubed. There you go. That's the same way as had you expanded out. Let's see if I can get it all on my brain. Had you expanded out this guy, starting with a 0, there's your 1, then started plugging in a 1, it's this guy, and then a 2, and a 3. Yeah, so either way, you end up getting the same answers. And I know the general one is usually harder for students to get, but okay. Let's give you a couple definitions that I'm not going to write out because we're really not even going to be dealing with these until tomorrow is when you'll see, on the next lesson is when you'll see where we deal with these. But definition, a function is said to be analytic at x equals x naught, so at this point, if it can be represented as a power series centered at x naught with a non-zero radius of convergence. So if either r is greater than 0 or r is infinity. Yeah. You'll see on the next lesson how we deal with those. And there's a theorem that states that if f and g are both analytic at x naught, then also at x naught that are analytic would be the sum or difference of the two functions, the product of the two functions, and also the quotient of the two functions, provided that, of course, your denominator can't equal 0. And so the result is that any polynomial function, here's a polynomial, all the powers on x, where a naught through a n are all real numbers, it's analytic for all real numbers. So any polynomial will be analytic for all real numbers. Any rational function, p of x over q of x, is analytic for all real numbers such that the denominator is not 0. So if it's a polynomial function, which is what we're going to see when we're determining if it's analytic, you're just going to be looking for when it's if the denominator, if there's a denominator function in there and that can equal 0. And then, this is worth writing. So remember the Taylor series expansions for e to the x and cosine of x and sine of x. Zoom back out. All right, so recall these guys, super important. E to the x, its Taylor series is found from going from n equals 0 to infinity of x to the n over n factorial. Well, that, when you start expanding it, right, you could just memorize that part, but when you plug it in, x to the 0 is 1 over 0 factorial is also 1, so it starts with a 1, and then a plus, and then you plug a 1 in, so x to the power of 1, and then you plug a 2 in, so x squared over 2 factorial, plus x cubed over 3 factorial, plugging in a 4, and it keeps on going like that. Yeah? Cosine of x. Remember, cosine is an even function, and so it turns out that it will be all of the even powers on x. They do alternate in sign, with the first one being positive. It's x to the even powers, and an even number is written by 2 times n, over the even factorials. Remember, cosine's an even function, so it was the even guys. They are alternating in sign, but your first one is positive, but you're plugging in a 0 there. So that means when you plug in 0, you have a positive. X to the 0 is 1, and 0 factorial is 1. So you start with a 1. And then when you plug in a 1, it'll be a minus x squared over 2 factorial. And then it's a plus. And when you plug in a 2, because it would be positive, x to the 4th over 4 factorial. And then a minus x to the 6th over 6 factorial, just by plugging in a 0, and then a 1, and then a 2, and then a 3, and then a 4, right? They only end up giving you all of the even powers over the even factorials. And then sine of x, remember, is an odd function, and so it also alternates in sign, with the first one being positive, and then it's x to the odd powers, and an odd number you get by 2n plus 1 over 2n plus 1 factorial. So when you plug in a 0 here, you get positive 1. 0 here will be x to the power of 1 over 1 factorial, so it's just x. Then when you plug in a 1, you'll have a negative here, and a x cubed over 3 factorial. And then a plus, because when you plug in a 2 here, that becomes positive. It'll be x to the 5th now over 5 factorial. Plugging in 0, 1, 2, 3, right? You have a minus, and then an x to the 7th over 7 factorial, and it keeps on going with that. And it turns out that all of these converge, all 3 of these converge for all real numbers, and they're analytic for all real numbers. So all of them converge for all real, and all are analytic for all real. So that's nice. All right, we'll continue doing some more of these in the next lesson. Hope you all have a fabulous day.